to the x squared y. So we've added just a little bit more to the same function that we just worked with in example 2. Again, we're still finding just the first partial derivatives. So I'll start with f sub x, and that means I'm going to be taking del x of x e to the x squared y. Looks like I'll have a product rule where my first function is x and my second function is e to the x squared y. So I'll write this out with the product rule. I have del x of my first, which is x, times the second, e to the x squared y, plus my first, which is x, times del x of e to the x squared y. Now I can go ahead and I can take my derivatives. When I take the derivative of x, I just get 1. So this is going to be e to the x squared y plus x. Now del x of e to the x squared y is e to the x squared y times del x of x squared y. And if I take the derivative of x squared y with respect to x, I'll get 2xy. And then I can bring that in here. So we'll get e to the x squared y plus 2x squared y, because I have that 2xy, I'll multiply it with the x that's in front, and then I get an e to the x squared y. And that's my final answer for that one. Now for f sub y, I will go back to the original equation and I will find del y of x e to the x squared y. This one is much nicer because x is just a coefficient since we're taking the derivative with respect to y. So I'll pull it out in front and focus on del y of just e to the x squared y. All right, so when I take the derivative of e to the x squared y, I get x e to the x squared y times del y of x squared y. Now the derivative of x squared y with respect to y will just be x squared, and that will come out in front and multiply with the x that's already there. So I'll get x cubed e to the x squared y for my final answer. Awesome. Okay, so that's one with two functions where we have to deal with a product rule for one of the derivatives. Now we're going to look at a function that has 3 variables in it, and we're looking at h of x, y, z is equal to yz e to the x all over x squared sine of y. Now here I need to find 3 first partials, h sub x, h sub y, and h sub z. I'm going to start with h sub z first because it is the most simple. And I'm going to show you kind of a little trick to help you focus your eyes. So if I want to find h sub z, I am taking del z on this entire fraction, yz e to the x over x squared sine of y. The thing to ask yourself is how much of this function has to do with z? Everything is multiplied, and there's one z hanging out there in the numerator. The rest of this is just coefficients. So I'm going to rewrite this as y e to the x on top, x squared sine of y on the bottom, times del z of z. Since those functions are multiplied, I can write them as factors of each other and focus on taking the derivative of only the part that matters. For our case, del z of z, which is 1. So my final answer here is y e to the x all over x squared sine of y. All right, I can do something similar for h sub y, but the parts that have y functions in them are just a little bit more. So I'm going to write this del y. We are taking del y. I'm going to rewrite my fraction right now as z e to the x over x squared times y over sine of y. So this isn't a different fraction. I'm just writing it in a better way for me to be able to focus on the parts that are functions of y. So the z e to the x over x squared, that can just come to the outside. And we'll focus on taking del y of y over sine of y. Now what we have to remember here is the quotient rule for derivatives. And the quotient rule says we take the derivative of the first times the bottom. All right, so I'm going to go ahead and write this out. I have the z e to the x over x squared times, now I have my fraction. So derivative of the first, del y of y times the bottom, sine of y, minus the top, y, times del y of the bottom, which is the sine of y, all divided by the the bottom squared, and so that'll be sine squared of y. Okay, so I haven't actually taken my derivative, I've just set up the quotient rule. So I'll go ahead and take the derivative now. This is going to equal, well, del y of y is just 1, so on top I have sine of y, whoops, I'm not done yet, hold on. I almost left behind my z e to the x over x squared times. Okay, now this fraction in the numerator, del y of y is 1. 1 times sine of y is sine of y, minus y times the derivative of sine of y with respect to y is cosine of y, and then all divided by sine squared of y. And the best I could do to rewrite this is to just multiply tops with tops, bottoms with bottoms. So this is z e to the x times sine of y minus y cosine of y. Notice I have parentheses around that whole binomial there. And in the bottom, I'll rewrite it as x squared sine squared of y. And this is my first partial with respect to y. The last one for this problem will be h sub x. And I'm going to do the same thing. I am taking del x, but I'm also going to rewrite my fraction so that I can focus on the x stuff. The yz from the numerator, that's just a coefficient. And the sine of y is just a coefficient now. And then times the x stuff. On top I have e to the x, on the bottom I have x squared. Okay, so it looks like I have another quotient rule. Of course I could rewrite x squared as x to the minus 2 and focus on it as a product rule. I'm going to use the quotient rule though. So the yz sine of y comes out to the front. And we're going to deal with our quotient rule right now. So we're looking at del x of just e to the x over x squared. Okay. Right. Yz over sine of y times the derivative of the top, del x of e to the x times the bottom, that's the x squared, minus the top, e to the x, times del x of the bottom, so del x of x squared, all divided by the bottom, x squared, all squared. All right, so now I'll go ahead and clean this up. I still have my multiplier of yz over sine of y times the derivative of e to the x is e to the x. So I have e to the x, x squared, minus, and then the derivative of x squared is 2x. So I have 2x e to the x. In the bottom, x squared all squared is x to the 4th. This will simplify a bit. Number 1, in the numerator, I could factor out an x and an e to the x. So I have yz x e to the x. That leaves behind an x minus 2. And then in the bottom, I have my x to the 4th times sine of y. And then notice that x and the x to the 4th, those will simplify. So my final answer will be yz e to the x times x minus 2 all over x cubed sine of y. Okay, so in this particular one, I bothered to simplify things or to factor things because I could see that something would simplify in the denominator and just make it look a little bit better. And that's it for my first partials for number 4. Let's see what we have in number 5. Oh boy. All right, so again, we're dealing with 3 variables, f of x, y, z, and it's equal to 2x squared y plus e to the yz plus root z times ln of x. So it looks like we need 3 first partials. Let's go for it. F sub x first. We are going to take del x of this whole thing. Del x of 2x squared y plus e to the y z plus square root z ln of x. All right, running through the terms. 2x squared y, the derivative of that with respect to x will give me 4xy. The derivative with respect to x of e to the yz is going to be 0 because there are no x's in there. The derivative of root z times ln of x will be root z times 1 over x. And I can rewrite that just one more time. This gives me 4xy plus the square root of z over x. And that's good. Now let's do the same for f sub y. We'll be taking del y of 2x squared y plus e to the yz plus root z ln of x. When we run the del y through the terms, the first one, 2x squared y, the derivative with respect to y will just be 2x squared. The e to the yz will just be e to the yz. And the last term is root z ln of x. There are no y's in there, so that is simply going to be 0, and we're done. That's what we get, 2x squared plus e to the yz. Last but not least, f sub z. We're taking del z of 2x squared y plus e to the yz plus root z ln of x. The first term is 2x squared y. There are no z's, so that's going to give me a 0. Plus the derivative of e to the yz, well, the e to the y is just a coefficient of z, so the derivative of z is 1, so we just have e to the y. Plus square root z ln of x. The ln of x will just be a multiplier, so we'll focus on z to the 1/2, which is 1/2 z to the negative 1/2 times the ln of x. And I'll rewrite this just one more time. This is e to the y plus, in the numerator I have ln of x, in the denominator I have 2 root z for my final answer. Okay, that one wasn't too bad. There were no nice tricks that we could play like we did in the last problem because there was a fraction in the last problem. So you kind of want to be on the lookout for where you can make things easier on yourself or where you just kind of have to brute force your way through it. Next problem, number 6. We are asked to find the first partial of f of xy with respect to x, and then we are asked to find that same first partial but evaluated at the point 2, 3. So let's see how that works. Our function f of xy is tan inverse of y over x. So I want us to recall first that d dx of tan inverse of h of x, so any function that's in there, will be equal to 1 over 1 plus h of x all squared, and then times h prime of x. Okay? So with that, I should be able to apply this to our problem in the multivariate case and see how that all works out. All right, so we're looking for f sub x. F sub x means we're going to take del x of tan inverse of y over x. All right, according to Calc 1 rules, this should be 1 over 1 plus, in parentheses, y over x all squared times del x of y over x. Okay, let's go ahead and rewrite this and take our derivative. So this is going to equal 1 over 1 plus y squared over x squared. The derivative of y over x is going to be y times negative 1 over x squared. Okay, and that's actually technically a fraction. It's negative y over x squared. So when I rewrite this, I'll write it as 1 over 1 plus y squared over x squared times negative y over x squared. And with fractions, when you multiply, you go tops with tops, bottoms with bottoms. And so this becomes negative y over, and that x squared is going to distribute to the whole bottom, 1 plus y squared over x squared, and become x squared plus y squared. So this is our f sub x of xy. Now they want us to find f sub x of 2, 3. That means we're plugging in 2 for x and 3 for y. So this will be negative 3 in the numerator, 2 squared plus 3 squared in the denominator, which becomes negative 3 over 4 plus 9, or negative 3 over 13. And that's our final answer for that one. Now, this is first partial derivatives. We do have to deal with the situation where we have more than one derivative, more than, I should say, a first derivative. We have second derivatives. So we have to know how to handle that. Before I get there, I want to talk about this Clairaut's theorem. It says that if f of xy is a function such that we have f sub xy and we have f sub yx, these guys right here, these are called mixed partials. I should say mixed partial derivatives. Derivatives. Okay, so if these guys are defined and they're continuous on a disk, which a disk just means some region of xy values that contain a particular point AB, then the statement here says f sub xy of AB will equal f sub yx of AB. And so we're going to use that to our advantage to kind of check our mixed partials. And you'll have to use it sometimes in the homework to prove Clairaut's theorem. So what this is saying, though, is that we have a guarantee of when we can say that the mixed second partials would be equal. And so when we're asked to find all second partial derivatives in any multivariate function, it means that we're going to be finding this f sub xx, f sub yy, f sub xy, and f sub yx. And we'll get to see what that looks like in the next example and the one after that.